If you or your team are interested in presenting during the TRX Webinar series, there will be a link to complete the request form at the end of our series today, or you can contact the America Makes TRX Webinar Series Administrator, Jason Thomas, directly. A few important notes before we kick off our series at the end of the presentation. There will be an opportunity for a brief question and answer session. If during the presentation you have a question, please submit it in the Q&A space on your WebEx screen, and I will ask it during the Q&A session. I will do my best to get all of your questions answered. Today's webinar is on building confidence with laser powder bed fusion additive manufacturing. Without further ado, it is my pleasure to introduce John Loreto of Renishaw and Dale Sillison of Sandia National Laboratory. John Loreto received his Master of Science in Materials Science and Engineering from Michigan Technological University, USA in 2017. John has worked in a variety of manufacturing and engineering environments, including materials analysis laboratories, primary steel producing, and additive manufacturing. He joined the Renishaw Inc. Additive Manufacturing Products Division, AMPD, in 2017 as an applications engineer focusing on process engineering and material development. John has several areas of expertise, including component metallurgy, laser parameter development, and material qualification. Recently, John has taken on the role of business manager for AMPD Americas, focusing on daily operations, strategic development, customer success, and industrial adoption of additive manufacturing technologies. Dale Sillison got his bachelor's in mechanical engineering technology and his master's in industrial engineering from New Mexico State University. Dale is a senior member of the technical staff in Applied Science Technology Maturation Department at Sandia National Laboratories in Albuquerque, New Mexico. He joined Sandia in 2014, where he worked in design engineering and nuclear facilities operation. In 2018, he moved to the Applied Science and Technology Department. Here, he oversees the advanced manufacturing capabilities, including laser powder bed fusion, lithography ceramic manufacturing, and femtosecond laser ablation. Using these advanced manufacturing technologies, Dale has successfully developed processes for internal development and production. John and Dale, without further ado, I'll now turn it over to you and your team.
Awesome, Jason. Thank you very much for the introduction. It's a pleasure to be here. So as you guys saw from Jason, my name is John Loreto. I have the privilege of presenting alongside one of my customers today, Dale Sillison at Sandia National Laboratories. So today, we're going to do a bit of a two-part presentation. I'm going to start off with the Renishaw context as far as how we consider utilization of metal additive in an industrial context. And then I'll end up passing it over towards halfway through the presentation for Dale to kind of give his interpretation of how they're implementing new technologies and quality systems into their metal additive manufacturing environment at the National Laboratory of Sandia. Okay, so as we allude to here, building confidence with laser powder bed fusion, LPBF Additive Manufacturing. So just to kind of get into it, I don't want to dwell on history too much. However, I think it's critical for everyone on the call to understand where Renishaw comes from and what its history is with metal additive manufacturing. I think it's important for that context moving forward in the conversation because it really sets the baseline relative to where we're coming from and how we think it should be adopted throughout the market space. Okay. So back in about 2011, prior to 2011 rather, we were an end user of laser powder bed fusion equipment at our New Mills, which is our divisional location over in the UK. With the equipment at that time, we were leveraging the technology, like 125XY type platforms, small laser systems, to develop Class 1 medical devices, specifically those in the medical dental arena. Things like crowns, caps, bridges, removable partial dentures, things of that nature. So a big dental application. We found that during the early days of this technology, we found the machines to be inadequate at being able to develop a quality product within a quality management system. So in 2011, we ended up adopting, i.e. buying the technology that we were initially using within our manufacturing environment. And since then, Renishaw is about a 50-year-old company. Its core practices are industrial metrology. And since that integration of the additive portfolio into our market space, we've been ever slowly increasing our metrology engineering expertise into the metal additive manufacturing environment. Some other details here just to kind of talk about that as we keep scaling. While we did buy technology in 2011, that integration has kind of grown us into our current Renishaw 500 series platform that's probably most prevalent in the market space at this time. And in addition to the hardware itself, we have a bunch of other secondary process monitoring and data management solutions that help enable that technology moving forward. Okay. So with that being said, as I alluded to prior, Renishaw has a long history of being a specialization, design, and manufacture of precision metrology equipment. So while additive certainly has a metrology aspect associated with it, you have to consider other parts of the manufacturing environment that are typically more common set in the chip cutting world. So things like CMM, touch trigger probes on machine tools, laser interferometers for machine tool gauging and axis alignment, gauging solutions, fixturing solutions, and things of that nature. So with those technologies, a lot of those have optical-based approaches to them from a design architecture perspective. And with that, it's allowed us to do a lot of work within the additive manufacturing space as it's relative to laser powder bed fusion because of our ability to drive a laser uniformly across the build platform, right? And by consequence of that design and engineering effort, the machines are quite vertically integrated, which ultimately end up having a reciprocal benefit across the manufacturing environment, rooted in the technology of laser powder bed fusion, starting that process chain from, i.e., the raw material development practice. Okay, so throughout the development of this company over its years, we've developed what we call a productive process pyramid, which is more or less a manufacturing process control methodology that arguably could be applied across all different sectors of manufacturing, whether it's raw material producing, laser powder bed fusion, machining, casting, what have you, right? And it's kind of just as it alludes to on the screen. It's a little bit self-explanatory, right? So you have a process foundation, process settings, and process controls, and post-process monitoring. Throughout my bit of this presentation, I'll go into a bit more detail about those discrete increments as this relates to metal additive. However, it's important to consider that this is, the baseline as far as how we consider setting up a regulatory framework to drive your quality management system inside a metal additive manufacturing environment. Okay, so this is a couple of key examples, like process foundation, just kind of get your head spinning in this direction, would be things like laser calibration. Process setting would be like what type of parameters you're going to leverage within the build process, and process control might be dosing percentage or powder humidity measurements, things of that nature. Post-process monitoring could be things like gauging or CMM inspection, dimensional artifacts after the build, or it could be things like tensile testing, empirical data type stuff, right? So just kind of think about that congressional pathway moving forward. So to enable that pyramid, if you will, Renishaw has provided our customers with a wide variety of use cases for each of those tools. Dale will talk a bit more about these in his bit of the presentation, just to kind of give you thinking about this in more detail. Quantum would be the build preparation software that we offer. That's for laser parameter development, laser assignment, slicing, scan path, tool generation, API distribution, if that's something that's necessary to you. So that's kind of the process control, process foundation type stuff, right? Now, Renishaw Central is like the Industry 4.0 type solution that we would offer. That would be enabling a data mining type solution. That's another bit. That's more on the end type validation or in-process control set point, so more on the top side of the pyramid. And then Infinium AM Suite, which is our in-situ process monitoring solutions, is more of the what I'll call the in-situ gauging type process, right? And again, we'll go into this in more detail throughout the presentation, but this will kind of get you in the mind of the pyramid, the tools that leverage that pyramid's principle, and how they apply across the product space. Okay, so functionally what we want this to do is within the process pyramid and the tools we provide is allow the end user to have a connected manufacturing environment, which functionally gives us what we would call a global data set. Now, another way to think about this would be a regulatory framework wherein which we can drive our quality process to develop a solution that's useful and intended for end use products in a manufacturing context, whether that's medical device, aerospace, industrial automation, that dental, that kind of a thing, doesn't really matter. But the context is there to have the tools to drive that solution that you come up with. So the examples that we talk about here are, machine prints a part, we take it out of the machine, put it into a gauging type apparatus, machine the part, gauge the part with a flexible fixturing solution. And functionally as well, we have a CMM post-process inspection. So whatever these tools end up being, this is just an example of a chip cutting additive manufacturing environment. But functionally, based upon your end use application, this could be anything. But functionally, the tools are there to provide that regulatory framework and guidance so that as you develop your production moving forward, you have a serialized output of those products, which then allows you to do validation kind of after the fact to continue that process, keep informing the manufacturing process moving forward. So functionally, it's a cyclical type environment, but our intention here is to provide you with those utilities to do that moving forward within your quality management system. Okay. So where we come in outside of being the OEM solution software provider for this whole process would be not only the hardware side and software side, but the support we provide the customer after it's installed, or even pre-application support development, that kind of thing. So while we're not necessarily product design experts, one of the unique thing about being an OEM in the metal additive environment is that one day I could be talking to an industrial oil gas supplier. The next day, I could be talking to a medical device manufacturer, and the next day, I could be talking to, a customer electronics supply heat exchanger type application, right? So design, we want to try to force people to design parts effectively, design parts to manufacture, design parts that leverage technology's ability outside of what traditional manufacturing can do. And once that bit is done, so to speak, right, that moves on to the process optimization step. And then Dale will dive into this in a bit more detail, where we have the tools and resources available to support the metallurgy, mechanical property characterization, refining surface conditions, making the machines run a little bit faster. That's where we can kind of come into play. Again, this is the process setting, back to the process pyramid type thing. And then once you have all these bits figured out, it's platform readiness, it's ready to go into the manufacturing world, it's ready to be put to the test and actually put into a rolled out production type environment. Okay. Now, as we think about developing a QMS for the metal additive infrastructure, I could have an hour presentation just talking about what you should do, what you could do. But what we mean to do here is just kind of show you some examples about how you could leverage this in your environment, just to kind of give you some confidence moving forward, right? So as we all know, we've been to many technical conferences that talk about failure modes of metal parts printed, but I think there are certain things we can consider and frameworks we can devise for verification and validation of the machine platform is doing what it's supposed to be doing moving forward, right? So of course, we need to consider things like mechanical architecture of the machine platform. How is it built? What parts was it built with? How are they designed? How are they manufactured? What's the supply chain like to back up those parts in the field? What's one machine versus the other one right off the same line, right? So there's regulatory framework in the sense of standardizations that we'll talk about later that kind of help drive that conversation, how to make sure we're comfortable with what we're doing. The next thing may be build file preparation. Are you using a API, using the end user OEM's slicing solution? Are you going third party, integrating it back into your platform? There's a lot of things considered in that regard. How do you have design history files for that model? How do you know the model is the same way every time? Okay, we'll talk about that in more detail. And certainly things like, scanning precision and local processing conditions due to part geometry. We've given many presentations over the years about how different thermomechanical models are related to the part manufacturing process based upon how large the part is. Printing something like a dental RPD frame would be a lot different than printing, a spine implant, which not let alone the material, but the processing conditions and things you would do for each of these situations will be uniquely different. It's important for us to consider those moving forward. Okay. Then obviously there's all the, extrinsic properties with the machine platform, things like the powder going into the machine, how well the machine is dosing the material, what's the spatter doing throughout the weld process, and how to consider this stuff moving forward relative to a gas flow consideration, how it's validated and confirmed and gives you confidence moving forward. Again, we'll talk about that more down the line here once Dale gets his bit kind of going in here. Okay. So let's go back to that process pyramid and more or less consider the controls we need to start thinking about for this process foundation set point of the productive process pyramid relative to metal AM. Okay. So in the process foundation, we would typically refer to this as like, say, calibrating the linear axis on the machine tool, making sure the ball screw lines up with what the encoder is saying, something along these lines. But in the context of AM, we certainly have linear axes if your machines have a gantry type system, or if they have a Z-axis encoded, Z elevator that you have to make sure is running at the right runout rate across the elevator sleeve, or if you have hop swappable build chambers, things of that nature. There are certain things you have to make sure that machine is lined up and willing to do from an access perspective, but it's also important to consider how the laser optics and mechanics of that machine platform are behaving throughout the manufacturing process. So this is where we really want to verify, i.e. calibrate the machine platform to do what it's supposed to do. So in laser powder bed, we're all familiar with things like scan field correction, beam focal offset, beam profiling, and power mapping of the lasers. And this, ever expands upon even further once you get into multi-laser type systems, but certainly optical system health checks and artifacts you may use to validate once you've verified the calibration is correct, to validate that you're doing the right thing. The parts come out correctly. This also considers, your incoming powder feedstock, which parameters you're going to develop moving forward. Again, back to the dental RPD or spinal implant type example. And then functionally, what are you going to do to set the foundation? What is the baseline for the mechanical test specimens? Okay, that's how we would consider that portion of the pyramid. Going up the line here, this is the process setting example. So this is that back to that build file control. How are you conditioning the wiper blades? How are you conditioning the filters? How are you making sure the build plates are put into the machine correctly? How's the wiper aligned? What is your set points in the build chamber for O2 set point, gas flow, recirculation rate, O2 settings, temperature of the gas flow? How well is it millivapor condensate condensing in the air within the gas plume? Those are all types of things you want to consider kind of moving forward and ideas to get your head spinning on. Okay. So in this context, relative to process setting and process control, this is where you start to look at the machine platforms themselves, where you start thinking about, okay, how can I control my process and set up my process in the beginning to ensure stable operation moving forward. Again, that requires a foundation to set correctly. You put in your settings that you want to drive and hold constant throughout the build. The green section in process control is maintaining those sections, okay? And then that's things like we have on the screen here, powder handling, dosing control, layer inspection for, this is the in situ process monitoring stuff. It gives us a flexible gauge capability and things of that nature. That's all the portions. This is like you can consider like the 1D sensor data that might come off the machine platforms, build plate temperatures, humidity monitoring within the powder chamber system, things of that nature. Flow rates of the chiller going through the optical banks to make sure they stay cool. This is all this type of stuff, right? Which is all available to you on a Renishaw platform, okay? Now, the last bit here, while we think about in the traditional AM context, is we always love having some type of empirical data, because at the end of the day, there's still a large volume of data work that needs to be captured and analyzed to be able to say, we can take an in situ process monitoring spectrum, if you will, and say that implies my empirical evidence and my tensile bars are correct, i.e. they're 1-to-1. That's an argument we'd like to push for, because I think that makes a lot of sense, as opposed to pulling a bar for every build that you do, but that's more of a long-term kind of a thing. But that's where we're kind of coming at, as we would offer solutions for you in that regard, to give you that functionality in addition to any empirical testing you may do moving forward throughout the manufacturing environment. Okay. So that's the pyramid. That's how we consider AM in the context of that pyramid. And now as we move forward, we're going to grab onto Dale here and let him kind of talk about how he's taking these tools that we've collaborated with him on moving forward. And ultimately, it was our guidance, but Sandia put together this protocol and this methodology with a regulatory framework and guidance from a industrial standard that drove their quality management system. And functionally with that quality management system, what's on the screen here is a very, Googled what a QMS means type definition. But functionally, it is true. If an environment and a company can adopt a quality management system that helps give them confidence with how to implement the technology within their environment, as opposed to trying to adopt someone else's, it's going to be more successful moving forward, because it gives everyone the warm and fuzzy feeling about the manufacturing process that they're all looking for. Okay, so I'm not going to read that to you. That's again a very Google-based definition of what you would find. But functionally speaking, now I want to kind of hand it over to Dale to let him kind of dive into Sandia a bit more and let him kind of walk you through how a end user of the additive equipment has actually leveraged the technical expertise of the OEM in conjunction with available aerospace regulatory frameworks, and then in conjunction with their quality management system that they already have built in at Sandia National Labs. Okay, so Dale, I'll toss it over to you now.
Thank you, John. That was great. Welcome. A little bit about, I kind of want to start off with a little bit about Sandia for those that don't know. So Sandia is one of 3 national Nuclear Security Administration Research and Development Laboratories in the United States. Our primary focus is to develop, engineer, and test the non-nuclear components of nuclear weapons. Seen here across is some of displayed images, not necessarily my images, just Sandia's images of some of the great accomplishments we've had and some of the access to tools and technologies available to us. Next slide. The motivation behind pursuit of advanced manufacturing. Advanced manufacturing, such as laser powder bed fusion, allows us to bridge the gap between development or product realization, test components, all the way into production. There's a large effort going into the labs right now to expedite many different things. I think we're seeing that across the United States and across industry is how can we make things faster, more robust, more reliable, and also have significant amount of digital engineering packages associated with that. So the tools that John talked about earlier, we are trying to figure out the best ways to capture these digital engineering tools to make sure that we have all of the right processes, all the right documentation, and all the right machine connections in order to gain the digital engineering information to help us build these processes to where we can understand them and we can mature them into a better product for our production needs or our development needs. Next slide there. So this year, it's quite an exciting year at Sandia. We will be stepping into from going from that long stretch of development into a qualified production status. So what that means for Sandia is maturing a part all the way up to where it's ready for deployment into our systems. We've spent the last few years researching and better understanding how we're making this product, why we're making it with laser powder bed fusion versus other technologies. Traditionally, in the past, it was a manufactured machine component. Laser powder bed fusion provides some opportunities for us to investigate that actually provided significant benefit towards our component. And it was designed specifically for this technology, using metal additive manufacturing, the layer by layer basis, as well as understanding what the surface topology or topography of that material looked like. And it enabled us, our product, to be beneficial to serve its function within the system. We've teamed with Renishaw, we've teamed with many people around the laboratories to make sure we understand all of the different attributes of controlling the machine, as well as understanding how we need to govern each one of the processes carried forward. We're also looking at what industry specification, yeah, you can go ahead to the next one, John. What industry specification best aligns with what we're trying to do. We kind of went out and surveyed all of the different options in industry. Typically at Sandia, we sometimes create our own specifications and standards, and sometimes we just mirror a lot of what industry's already done. We feel like AMS is the leader in laser powder bed fusion, stepping out forward, making a specification specifically for metal additive manufacturing. That is intended for aerospace manufactured components. This is really representative of the components that we are looking to make. So it aligns very well. And the one that we've chosen that chose kind of talk about in the framework here that we're talking about is AMS 7003, laser powder bed fusion specification, processing specification. There's a lot of other AMS documents that we're referring to throughout our qualification process, but this is kind of one that's governing most of the work that I'm doing in my lab. As Jason mentioned at the very beginning, my role and function in this position at Sandia is to operate the laser powder bed fusion facility and provide very capable and qualified parts to meet the customer's demands and requirements. In addition to that, I not just to support a production effort, but to support development components, research components across the laboratories. So I'm not the material scientist behind some of these parts, but I make a lot of components for material science to help me evaluate and understand what the maturity of these components are, or what impacts some of these settings that are capable or available to us through these operating systems, how they go into the components. So next slide. Probably a question some in the audience may have is why adopt AMS 7003? We do understand that there are other specifications available in the industry, but we chose to adopt it because we felt that it meets it's within our mission space. It meets the requirements of our manufactured components. To date, it's the primary contributor to the MMPDS database. All the data from MMPDS, or all the data published by the SAE has went into MMPDS. We also have evaluated the NASA 6030 specification. Some in the audience are probably familiar with that specification. However, we found that to be very restricting, and it's very hard to meet all of the requirements of that document, but it didn't provide the leeway that we were looking to have when we were trying to qualify our components. And with the materials and equipment we had available within these, or with the machines that we had available, the limited number of machines across Sandia. I did mention here our lead qualification engineer or expert is Tyler LeBron. He's a Sandia lead. He's readily available and he's happy to discuss more of the qualification efforts, and he's a subject matter expert serving on many different communities to help Sandia be capable of qualifying metal additive components. So I've kind of wanted to take AMS 7003. I'm not sure how much familiarity the audience has with the specification, but kind of break it down. And I highlighted here just exactly coming out of the specification, what some of the key things that we are looking to make sure that we're capturing, to make sure that we're documenting in accordance with the specification. So I'm not going to go through each one of these bullets throughout the presentation, but I did want to highlight the two sections that I felt were really critical. So section 3, it's the technical requirements of the document. It's really the heart and the meat of the document. It's where we're going to find out what are the key process variables. What things can I change in the Renishaw AM system that are going to impact my process settings down the road, or impact my material performance, the structure of the material that I've just manufactured. What is allowable for a process interruption? Can the build plate, can I shut the build off and then turn it back on? Or if I have a interruption in the process, am I capable of surviving that? Again, a good configuration management control system. We have digital file management all the way through software configuration control to really understand how at Sandia, how we're going to implement these processes and make sure that we can meet all of the requirements to have historical reviews performed on these manufactured components. The maintenance plan, I think with all manufacturing equipment, the better it's documented, the better success you're going to have. So we're establishing quality maintenance plans that are both capable of being performed either by our in-house technologist or service from Renishaw, the corporation, to come in and help us make sure these machines are capable of meeting the desired specifications. The little bit going down onto the machine approval and the process approval, this is kind of governed more towards the design agency. So serving as a production agency versus a design agency. In AMS document, it's mentioned a little bit differently, but internal to Sandia, we kind of set it up as we have a production agency that does the producing of the components and the design agency that controls it. So we work day in day with the design agency from a production standpoint to make sure that we are meeting the needs. And what information are we going to gain through these processes that we can run a statistical analysis on to make sure that we have a repeatable historical document controlling process. Next slide. So again, here, one of the highlights of this document to me, and it was quite exciting to see all of the things that they've already identified as key process variables. And from an operating standpoint, from a facility operations standpoint, it really makes you think about how am I going to make sure that I'm meeting all of these requirements. Some of these are discrete, and some of them give you a range of values that you can obtain, but we need to put controls on each one. So we have to really dive into each one of these settings. Not necessarily the build file or the build configuration, but we have to dive into a lot of the machine variables that some people just take that for granted. And when you were trying to qualify a process, you may or may not think about all of the different process variables that you have access to, or that can be impacted by a minor change. John mentioned earlier some of the software control. That's something that we're going to care a lot about through this process. So as we develop these components, we have to understand what the software is, how the software is slicing the files, what the raster patterns look like, what the Renishaw gives us the option for a couple different variables to create a velocity vector in the associated scan. So we want to make sure that we are not changing something just by a version control of the software. So we will team with Renishaw, or we will lock down the process to understand the revision change from one version to the next that controls these machines. And we'll also look at it from a layer by layer slice view standpoint, and we'll have to do that comparison whenever it comes to manufacturing these components. Some of this might already be old news for those in the audience, but for those that are not looking at that level, we want to make sure and understand each one of these aspects of these key processing variables. Our design engineering team is looking at this to make sure that they have a quality product delivered from the first batch of parts that we make all the way to the last batch of parts that we make, that it is extremely repeatable, that they understand what's happening within the system so they can make decisions that on their qualification decision that as it goes into the system. So how are we meeting some of these? Maintaining configuration control. I kind of mentioned that earlier. So this is just one configuration control map for a specific component that we've chosen to go into the manufacturing process. So we're going to start at the very top of this tree diagram, and we have the what we're calling the definition of it. So all of the information associated with this is going to feed into our component specific specification. And so we have a bit of the additive manufacturing, the model specifically. So we're going to have to control these. We're going to have to put these into a database. We also have the common specifications. It's going to tell us what type of surface finish is allowed, what kind of radius, minimum, maximum radius we can have within these components. We also have all of the powder specifications, what type of witness coupons we are using, some of the AMS documents that are associated with the process that we're using, and how we're going to adopt those into making our specific use specification. And this is just for one specific component. This is not to qualify every component at Sandia, but this is just one component that we've identified and some of the things that we're doing in order to make sure that we have repeatability and consistent processes when manufacturing this component. Kind of highlighting the specific use specification. So we are, again, we're aligning it very closely with the AMS 7003. We are associating all the key process variables and making sure that we capture and meet every one of them. It also contains what all of the specification is going to contain the required inspection aspects of this component. So John mentioned earlier the capability of CMM or metrology equipment, as well as the inspection of our tensile performance or the identified witness samples that we're going to have placed adjacent to our component on the build platform. We are going to control the build layout, so we have consistency from build to build to build. If there's 15 components or 45 components on the build plate, we will have exact location, tracking, trending of every one of those components, dimensional performance, and historical performance as far as in a functional test of the component within the design. The build plate requirements, we also want to talk about that. So if there's anything associated with the build plate, we have to make sure that the material of the build plate is consistent with the material we're manufacturing onto it. We want to make sure we understand how many times the build plate has been through the process, what kind of thermal processes we need to go through in order to make sure that there's no deterioration of the build plate as it goes from one build to build 5 or to build 2. And in the event that we see any changes within that, we would want to capture it and make sure that our customer is well understanding of the potential impact that the build plate performance could have. Again, I mentioned component identification and requirements. So I think that carries the next slide, please. So here I want to talk a little bit more about software control. Some in the audience may be familiar with the Quantum AM software. Quantum AM software, in controlling the Renishaw 400 systems, it gives us a lot of flexibility. I believe last time I counted, there's 138 different process settings in the Quantum software that we have access to. So we're going to go through and we're going to manipulate all of these 138 different variables to make sure that we can deliver that quality product. So we go through these build layouts, and what you see on the top left is essentially just an experimental setup to test Sharpie impact testing as well as tensile testing. I believe there's some EBSD samples on the same one. So we build these material libraries on the right side here that you see. A lot of these are self-published or published from Renishaw, and they have a great understanding of how these tools operate for a specific material. Whether it be 316 or titanium 6.4, we're taking their base parameter sets and we're manufacturing many components using their base parameter sets and slightly manipulating the process settings to mature these into a fully manufactured component, controlling all of the location as well as all of the settings associated with the laser process settings, build process settings to manufacture and control this. I put software control here because once this is done for the production ready components, this will be a lockdown process. We will not change this through the life of this program or through the life of this duration until the next cycle and it's evaluated. Do we want to understand how we want to change it? Next slide. Mentioned earlier about calibration and maintenance. This is one of the key the key process variables that we want to make sure we understand and control. We team with Renishaw in doing a lot of the calibration and maintenance. So directly from AMS 7003 Appendix B, it gives you a very good outline of what the minimum measurement requirements are. In each one of these, it talks about each one of the requirements, we have to have a very solid documentation on how we meet these and how we will obtain quality certification to make sure that we're meeting these not only with just the standard methodology, but also with calibrated devices, calibrated measurements to meet each one of these requirements and have this in a historical document to where when we go into production, we understand the requirements of these components. Next slide. Oh, let me go back one more note here on the calibration and maintenance. You can see on the right is a laser view. So we're verifying the optics of the image here. This is also going to provide us if there was an astigmatism associated with our laser optical train, were any deviations from normals. That's, if you're not familiar with seeing these type of graphs, we're looking for intensity as well as power, and we're also want to make sure that we have within this that we're not seeing any deviations associated with just this one calibration metric for this process. On the bottom left, you can kind of see there are adjustments for our power curve and what we're seeing, where our focus is at within the machine. Pretty common stuff in laser powder bed fusion, but if you're new to it, these are a couple things that that we're going to make sure, or the table on the left is we're going to make sure we identify all of the processes and how we align with this. Some of these can become quite challenging, and I will talk to that in a little bit. How do we make sure and measure this? We are using a little bit older of machine. We're not using the Renishaw AM500 system, so we are qualifying this process on an AM400. So we have to be pretty creative when it comes to meeting some of these requirements, and I'll talk to that in the future slides. So calibration and verification. So how do we verify that what we just tested is capable of meeting our needs and historical performance? So you see on the left, we have a build plate full of witness samples that we print at a standard location. That allows us to come back in and check repeatability of the print, check consistency of the material performance across all of these samples. There's a large number of test samples here. I believe, I don't want to specify which samples they are, but they're approximately 2 inches tall, just tensile pull samples. On the right side, we do a lot of single bead calibration. So on the right, you can see this is just a single track bead, and we go through and we do these just on a base plate of material, and we can get a lot of information here. We can understand how the laser is interacting with the specific material we put underneath it. We can also check it for consistency. On the bottom image, you see I believe there was 480 different scans performed on this one single bead test, and that allowed us to go back and say, okay, well, we're seeing the same consistency when we command the laser to go from left to right, from top of this plate to the bottom of this plate. We see consistency. So every time that we say we want to operate at 1 meter per second at 200 watts, we can generate a laser scan across this, and we can ensure consistency across the build platform. And then we can also cross section the laser interaction across this and see how much penetration we have with the laser, as well as beam characteristics, to make sure that it's normal throughout the process. We're not seeing any deviations across that. Next slide. I mentioned earlier some of the things that are hard to capture as far as a calibration. The Renishaw AM systems do not contain a in situ monitoring capability that's either video based, or they're limited on their in situ monitoring. They do have a little bit of output data that we can get from build files. But what I'm showing here is we came up with a method to better understand laser velocity. I'm not showing the speeds or the timing here, but we're using acoustic signatures that are helping us to better understand. Hey, we commanded the laser to move at, say, 1 meter per second. We can hear acoustically when the laser turns on, when the laser turns off, and we know the exact distance that it travels. So therefore, we can infer that we have the velocity captured of how long the laser. More refined measurement of that timing that we would see as far as a recoder speed. So we can acoustically hear when the recoder starts to move, and we can hear when it stops. So we have a really good timing. We can understand. We might tell that up here in the user settings, we might command the recoder to move at a certain speed, but now we have consistency, and we can understand that from build plate to build plate, or from calibration effort to calibration effort, that we have consistency across these machines. Next slide. So I mentioned earlier kind of the process framework that we have for a specific component, but kind of going into the facility requirements, we have to develop from the design agency. They develop a lot of framework on what this component will do and how it's going to do it. In my facility, here's some of the things that really come to the top of my list on what I want to make sure I am capturing to make sure that the component is repeatable from process to process. So I have the process qualification report on the top left. That's an independent document that all of this information feeds into. We're going to set up we already have established operating procedures, pretty common with other facilities or pretty common in the AM facilities. But these five key steps that I've identified as where we're going to that align directly with the AMS 7003 documentation and the AMS 7032 documentation. So we're going to take and break these into 5 different segments. So we have printer operation, we have powder handling, removing of the powder, separating it from the build plate, and then dimensional inspection. Not covered in here is the thermal treatment, but that could be as part of the separation of the build plate. The printer operation, it's more than just hitting print, right? So I want to make sure not only do we have all the right documentation, but we also have all the right operator qualification that directly ties into AMS 7003, all of the right parameters, and there's no change from process to process. We're going to also verify our powder handling is consistent. So how do we verify that the powder we have coming in meets all the requirements of our internal powder specification document? We're going to have sampling throughout every build for historical reference. We're going to sample every time we get a new batch of powder in for consistency, and we'll send these all. We'll have either internal analysis performed, or we'll work with other agencies to conduct analysis on their powder for consistency. These are some of the framework that we have set up to allow us to produce these components within our lab. The next slide is really the highlights of a requalification or the process verification, process setup verification. So directly another highlighted area, I think a key area of AMS 7003 is we have the requalification. So in the event that we have to move the machine, we have to switch machines from one Renishaw to a different machine. We have historical documentation. We have the guidelines and outlines for our future to what we need to do in order to document it to where we can make these changes. In the event that we have a facility event, we lose the air conditioning or the air handling system. Building events, we lose power. These type of things can be directly impactful to a component. And how do we recover from that? And how do we make sure that we don't need to go through the full requalification effort? But these are all documented. And I just want to highlight here the sections of AMS 7003 that are specific to, I think, some of very, very key attributes of this spec. In addition to section 3, it's really creating the evidence to make sure that you have a qualified process and you are aware that things that can impact your process into the future. I think that covers the majority of section 5 here. And the last thing I have is, next slide, John, is just thank you. Thanks to the audience for attending. I hope that you got a little bit of insight from this presentation. My contact information is here. Please feel free to reach out if you have any questions. I'd be happy to speak more with you on some of the things that we're doing and how we're meeting the qualification of our internal components.
And thank you again, Dale.
Sure.
Very much appreciated. Yeah.
All right. Well, hey, I want to thank John and Dale again. That was a great presentation. We'll now head into the Q&A session. If you have questions for our presenters and you haven't done so already, please type it into the Q&A box, and I will do my best to get them answered. Okay, so let's see. I got one question here. All right, thank you for the presentation. Oh, hold on 1 second. Sorry about that. Okay, thank you for the presentation. Will you be only using virgin powder during qualification? Will you be continually testing moisture content in your powder feedstock?
So the initial test of this component, as we go through our initial development, we will be using virgin powder only. In the event, as we study and characterize and understand the performance of this powder, it will determine if we have the ability for reuse. I have reservations, as probably many in the industry do. This component that we're manufacturing, I'm sorry, I cannot display the component based on the nature of the work, but this component lends itself very well to using virgin powder for the manufacturing due to the size and the height of the component. It's not a big burden or a big cost savings to not use virgin powder for this. But this type of data is going to allow us to trend over time to see what the historical performance and the quality of the powder and how that powder stays consistent from batch to batch, or if we do have any oxygen pickup or moisture contamination. The other thing that a lot of people, I think there was a recent published article that talked about not only moisture content or moisture pickup, but also internal contamination. So as we process these components and the operators, the technologists manufacture these components, we have to be very aware of their potential to introduce foreign contamination into the manufacturing process that is oftentimes ignored. So if it might be a rubber glove, it might be a bristle from a brush that we have that can directly impact the quality of the next print, and it might be completely overlooked by many things that are not being addressed. So as for right now, yes, I am planning to use virgin powder for this production process with the intent in the future to look and make sure we have enough statistical information to qualify and say we can reuse it.
All right, great. Thank you for that answer, Dale.
Sure.
All right, if you have any other questions, go ahead and get them in now. You guys must have done a great job because we didn't get many questions. So let's see. If we don't have any other questions, if I don't get any in here, that is going to wrap up today's TRX webinar series. Once again, I'd like to thank John and Dale. That was a great presentation. If you do have further questions for either of these gentlemen, you can reach out to them directly. I see John's contact info is on the screen here, john.loretto@renishaw.com. And you guys want to go back one slide so we can show Dale's contact also. So if you have questions for Dale, you can reach out to him there. All right. So I don't see any more questions coming in or comments. So
I'd like to thank America Makes for hosting this, and thanks for the opportunity to come and join this session. It's been great to work with John and Renishaw. I think the success of this teaming arrangement has been instrumental on providing us a qualified production component that we're going to be deploying soon.
Awesome. Well, thank you, Dale. And thank you, Jason. Appreciate it.
Anytime, guys. Thank you. All right. So there's going to be a post-webinar survey going out to all of those who participated. We really do appreciate the time that you take to provide America Makes feedback. That way we can continue to improve and strengthen this additive community. And as a reminder, if you think that you or your organization would be interested in sharing in a TRX webinar series, please fill out the form that follows the presentation, or you can reach out to me at jason.thomas@ncdmm.org. Thanks, everyone, and have a great afternoon.